This is an extremely important section because throughout the rest of the chapter, you need the ability to simplify square roots. A square root expression is considered to be simplified if it meets these three conditions. The first is that the radicand contains no perfect square factors. And if we look at this example, the square root of 8, 8 contains a perfect square factor. If you go to your list of perfect squares, 4 is a perfect square and it is a factor of 8. The square root of x cubed contains a perfect square factor because, remember, even powers of variables are perfect squares, and x squared then is a factor. So these are not in simplified form. The second condition is that there can be no fractions under the radical. Here we have 2/9 under our square root symbol. Therefore, this is not in simplified form. And the last one sounds very similar to the one above, but it's actually different. There can be no radicals in the denominator of a fraction. So we can't have an entire fraction under the radical. We also cannot have a radical in the denominator of a fraction. It's okay if it's in the numerator, but not the denominator. Let's recall we have the product rule for square roots, which says if the square root of a and the square root of b are non-negative real numbers, then we can say the square root of ab equals the square root of a times the square root of b. Now there are times when we have them separated and we want to push them together under one radical. We can do that. When we simplify, we actually have something that we're going to want to pull apart. Similarly, we have a quotient rule for square roots. If the square root of a and the square root of b are non-negative real numbers, and b does not equal 0, then we could say the square root of a over b equals the square root of a over the square root of b. In other words, we can pull apart division and give them their own radicals. Or if we have them separated and we want them together, we could push them together. That's very powerful. We cannot say that the square root of a plus the square root of b equals the square root of a plus b. We don't get to do that. We can't pull apart and push together addition or subtraction, but we can with multiplication and division. So let's look at our procedure now for simplifying square roots. And the example we're going to use is here, the square root of 24. If it contains any perfect square factors from our list, and let's just throw those in. 2 squared was 4, 3 squared was 9, 4 squared was 16, 5 squared was 25, 6 squared was 36, and on down the list. If this number under here contains any of these as a factor, in other words, do any of these divide evenly into it, then it is not in simplified form and we need to simplify. Well, 4 divides evenly into 24. So this is not in simplified form. So the first thing we're going to do is look for the largest perfect square factor, really. And we found it. We said the square root of 24 is the square root of 4 times, well, let's see, 4 goes into 24 6 times. We're going to use that product rule now to rewrite this as a product of two radicals. Always perfect squares go in your first radical, remaining factors go in the other radical. We said 4 goes into 24 6 times. So we've pulled apart 24, it's 4 times 6. We made certain to put all our perfect squares in that first radical. And now we can take the square root of the perfect square factors in here. And we really engineered this so it has all perfect squares, so we could take the square root. The square root of 4 is 2. And we can't do anything with this, so it just stays. I tell you to check to see if there are any perfect square factors under the radical, and the reason is sometimes students don't manage to get the largest, and you need to double check and make sure are there any more perfect square factors in there. If not, you're done. If there are, then you did not find the largest and you have to repeat the process. Okay, so we want to simplify the square root of 32, and I threw in the 2 radicals here to make it very clear. I want to see 2 square root symbols. I want perfect squares in the first and whatever's left in the second. Now, I can see that off my list 4 goes into 32 8 times. I know that's not the largest. How do I know that? Because 8 still has a perfect square factor. In fact, 8 has the factor 4 also. It's 4 times 2. So I didn't find the largest, and now looking at this, I can actually see the largest. If I break it down like this, I can see, well, a perfect square times a perfect square is a perfect square. So 32 is 16 times 2. 16 is the largest. And notice 2 contains no perfect square factors. So 16 and 2. What's the square root of 16? 4. 150. Well, students tend to know money. And 25 goes into 150. How many quarters does it take you to make up $1.50? Well, 25 goes in 6 times. And of course, the square root of 25, well, we engineered it, so this is a perfect square in here, so we could take the square root, and we get 5, square root of 6. 1,200. Well, I see 100. 100 times 12. Is that the biggest perfect square factor? Does 12 have any perfect square factors? It does. 4 goes into 12. 100 times 4 times 3. Okay, this is a perfect square. This is a perfect square. If we multiply all this, we do get 1,200. Does 3 have any perfect square factors? No. So the product of these 2 perfect squares is going to be the largest perfect square that divides evenly into 1,200. And that's 400. So, perfect square factors and whatever's left. We said 400 was the largest perfect square factor, and 400 times 3 equals 1,200. What's the square root of 400? Well, you probably don't know that one off the top of your head, but you could use your calculator, and you wind up with 20 times the square root of 3. Okay, here we have 4 square root of 18. That 4 stays with us. But 18 has a perfect square factor, so we need to simplify this square root. What's the largest perfect square that divides into 18? Well, 9 goes into 18 2 times. So we have 4 times, and of course we could take the square root of our perfect squares, and we get 3. Times the square root of 2. 4 times 3 is 12, so we have 12 times the square root of 2. In this problem, we have a negative out front. In fact, we have a negative 3 out front that stays. But 50 does have a perfect square factor. 25 goes into 52 times. So we have negative 3 times, and of course we could take the square root of our perfect squares, and we get 5, times the square root of 2. So that's negative 15 times the square root of 2. In this last example, we have a huge number. I have no idea what the largest perfect square is. So this is where I'm going to look for a perfect square that divides into it. And I can see that 4 does. If 4 goes into the last 2 digits, which is 20, then 4 goes into the whole number. So let's see. It's going to be 4 times 1080. Well, 4 goes into 80. I can do that again. We have 4 times, and now we're breaking up 1080. That's 4 times, let's see, 8. We're left with, okay, 70. Do we see any perfect squares that divide into 270? Well, 9 goes into 27, so it's going to go into 270. So 4 times 9. And we take our calculator, we divide 270 by 9, and we wind up with 30. Are there any perfect squares that divide into 30? Well, the first perfect square is 4. That doesn't. 9, no. 16, no. 25, no. The next perfect square on our list is 36. And it's larger than 30, so we don't even have to look any further now. Incidentally, what do we do on our exam if we get a little anxiety and we can't remember our perfect squares? Well, we take our scrap paper immediately and we write a list of all our perfect squares so we can refer to it while we're taking our exam. Okay, so our the largest perfect square that divides into this number then is going to be the product of these perfect squares. So we have 16 times 9, which is 144, times 30. Here's the largest perfect square. That goes into 4,320.